Dear friends, in this video, we will learn about balancing of rotating masses in several planes. It is highly recommended that all the viewers of this video should have seen my earlier presentation video on balancing of rotating masses in one plane, because that video is fundamental to this video. Hence, please go and watch the earlier video. Let us start with methods of balancing. There are two methods of balancing depending upon type of equipment: static balancing and dynamic balancing. Static balancing is done when the components have a very small L by D ratio of the order of 0.25, where several masses are rotating in the same plane. Whereas dynamic balancing is done when the components have large L by D ratio more than 0.25. Balancing of several masses is done when the masses are rotating in different planes. Let's try to see condition. For example, the impeller and the fan shown over here. These are planar components where L by D ratio is very small, and in such cases we go for static balancing, which we have dealt in the previous video. And for the components like this, where there are large length and small diameters, we go for dynamic balancing. In these cases, we find that there may be some unbalanced masses in different planes rather than in one plane. For example, you see the red dots that I have shown. These are some unbalanced masses which cannot be seen with naked eyes. They are present within the system because of manufacturing inaccuracies. So we will learn how to take care of such conditions, or how to balance such cases when the unbalanced masses are in different planes. This kind of balancing is known as dynamic balancing. For simplicity, we'll first understand taking one mass. Let us consider that there is one unbalanced mass on a rotor. Let us say this rotor is turning with some speed and the rotor is supported on two bearings. Let us assume that we have provided one balanced mass on the opposite end exactly at 180 degree. Then it can be balanced. But consider condition if we provide a balanced mass in some other plane. If we do that, then we'll generate some couple, and this couple has to also be balanced. So we generate a couple unbalanced which is required to be balanced. This couple will produce forces on the bearings. So in such cases we have to go for dynamic balancing. That means we have to balance force and we have to balance couple together. Let us consider one mass mu at radius r. Let us say that the shaft is turning at angular speed omega. Then this will generate a centrifugal force radially outward, which is equal to mu r into omega square. If I provide some balancing mass mb at radius rb, and this is also turning at omega, then this will generate mb rb omega square. But because they are not in the same plane, they will generate a couple. So because of this couple, the force which will be acting on the bearings will be mu into r omega square, small l, which is the distance between the two masses, and capital L is distance between the bearings. So this kind of forces are generated on the bearing. Because of these forces, the bearings may fail and there may be a lot of vibration, and that is why we have to go for dynamic balancing. Now let's try to understand what exactly happens when the shaft is not dynamically balanced. Let us say that this blue line is showing the axis of rotation, and the red line is showing the axis of center of gravity. Then center of gravity becomes inclined to the center of rotation, and in such cases there will be a couple generated, and because of this couple there are unbalanced forces on the bearings. So our aim is to balance the unbalanced couple and to balance the unbalanced forces. So let's try to understand how we can mathematically deal with the problem. Let us say this is a shaft. On this shaft, let us assume that there is one unbalanced mass A in a plane A. Let us say that it is generating the force Fa. There is another plane B which is at a distance, some distance from A, and there is another mass which is at some other angle considering A, and the force generated is Fb, that is in the radially outward direction. We consider the third plane C which is at some other distance from A and B. There is some mass which will generate a force, radially outward force or centrifugal force Fc, and there is one more plane D in which there is one more mass Md, and that is also generating a force Fd. Let us notice that there are four different planes. In all those four different planes, there are four different masses Ma, Mb, Mc, Md, and each mass is at radius Ra, Rb, Rc, Rd, and each is at an angle of theta A, theta B, theta C, theta D. Normally, theta A is taken as 0. So we have to now balance the couple as well as force. To balance this, let us assume that there is one plane L and there is one more plane M. Our aim would be to provide masses in the plane M and L at certain radius such that the all the forces and couples are balanced. So we'll see how we can do that. It is known as dynamic balancing. There are once again two methods, a graphical method and analytical method. We will first go for graphical method. Let us say that the A, B, C, D are in some planes. Let us say that there is a plane L which is known as a reference plane. There is another plane M which is at a distance D from the L plane. Let us say that we have taken reference plane as L, then LA is the distance between L and A. Distance between L and B is LB. Distance between L and C is LC. Distance between L and D is LD. So these are the distances, and now we try to see some masses. Let us say that there is a mass MA at a radius RA. Let us say that there is a mass MB at a radius RB at an angle theta B. There is another mass MC at a radius RC and an angle theta C from horizontal, again measuring anticlockwise sense. There is another mass MD at a radius RD, angle theta D, again measured in the anticlockwise sense from horizontal. Now we are going to put one mass MM at a radius RM and another mass ML at a radius RL at some theta M and theta L such that we dynamically balance. That means we balance the couple and we balance the force together. To solve this problem, we'll first prepare a table. This time there are 7 columns in the table. If you recollect my previous presentation, for static balancing we had 5 columns. The first one is the plane, the second column is mass, third column is radius, fourth column is M into R, which was there in the previous also, and the last column was angle. This time we are adding 2 more columns. One is distance from the reference plane L and second one is the column. So we have added 2 more columns in this table, and now we'll go plane wise. Plane number A, B, C, D, L and M. So let us try to enter some unknown data right now and try to understand how do we solve the problem. So let us say that Ma is the mass, Mb is the mass for B, Mc is the mass for C, and Md is the mass for D. So whatever digits or alphabets I show in black color is the known data, and whatever are shown in red colors are unknown data. So in this table, if you see the first row, ML, the unbalanced must be provided, balancing must be provided in in the plane L is ml and balancing mass to be provided in the plane M is mm. So that is the unknown data. Now let RA, RB, RC, RD are known. Let us say RL and RM is also known to me this time. Now knowing these two columns, we can very well find out the fourth column. MARA, MBRB, MCRC and MDRD can be calculated, but the other two are not known, so let us put them in the red color. Now to decide L, we have to first decide a reference plane. For no reason, right now we are deciding L as the reference plane. Slowly we will understand as we solve the problem which is to be considered as a reference plane. So let us say that L is the reference plane over here, and you can see over here the L is the reference plane, and therefore LA becomes negative. And therefore we put a negative value taking a reference plane, and ML, this point will become 0. So L plane distance would be 0 and mass of A from L plane will be minus LA, and distance of mass B from L plane would be LB, and then we have to show distances of all the masses and all the planes with a reference to L plane. So 0, LB, LC, D and LD. In this problem we'll assume that D is also known to us. Then we can find, now knowing MR and else, we can find MRLs. So we can find this column, MRL column. So like this we can find MRL column. MMRMD is not known because MMRM is not known, and MMRM is not known because MM is not known. Now angle thetas for A, B, C, D are available, so we'll add the angles for A, B, C, D, and remaining angles are not available, so we put them again in red. Now we go on to the next phase, how to do the remaining procedure. We'll make a couple polygon and a force polygon. So let's go ahead. Using the previously made table, we'll first prepare a couple polygon, and to prepare a couple polygon, we'll start with the last two columns. So we pick up the last two columns. The procedure for making couple polygon will be same as that we have used for the force polygon. We'll start with the horizontal line at 0 degree. So at 0 degree we have to draw a vector which is corresponding to the value of MARALA, but this time the negative sign shows that I will not be drawing the arrow towards the right, but we will drawing the arrow towards the left. Then the next row is 0, so we don't use it. We go to the next MBRB LB at angle theta B. So we recollect our procedure of drawing the vector. To draw the next vector, we have to use the arrow of the previous vector. So we use arrow as the previous vector as a reference. We take horizontal line as a reference and move the angle in the counterclockwise sense, or we measure the angle in the counterclockwise sense. The length of CB will be corresponding to the length to the value MBRB LB. Then once again we go for MCRCLC. The length of the arrow will correspond to the magnitude MCRCLC. The angle will be theta c, measuring from the horizontal in the anticlockwise sense. Again you should notice that the next arrow was made from the arrow of the previous vector. And with the same procedure we will draw MDRD LD. Now we are left over only with the MM, RMD and theta M, which we will get by joining the last arrow and the first tail of the first vector, and the length of this arrow will give me MMRMD. So from this value we will know MMRMD and MMRMD, and because D is known we will find MMRM. So now if you see carefully, see in this table MARA, MBRB, MCRC, MMRM and MDRD are known. What is unknown is only MLRL. So once we make a force polygon we will obtain MLRL. So let's go ahead and we now start preparing the force polygon. This time we'll select the fourth column and the seventh column. The fourth column will give you MARA, MBRB, MCRC, MMRM and MDRD, and the last column, that is theta, will give me all the degrees for all the vectors. So we'll start with MARA. So MARA is horizontal, so we draw a line which is equal to the length corresponding to MARA at 0 degree. This time we have drawn in the right direction because there is no negative sign. The next vector to be drawn is from the arrow of the previous vector, that is MBRB. So length of this vector will correspond to MBRB, angle will be corresponding to theta B. We once again remember that we are drawing the angle vector at an angle of theta B from the horizontal line and measuring in the counterclockwise sense. Now the next vector will be drawn from the arrow of the previous vector, the length corresponding to MCRC at an angle theta C, the fourth vector MDRD at an angle theta D, and MBRB at an angle theta M. Finally, we will connect the arrow of the last vector and tail of the first vector, and what we get is MLRL, and we'll along with that we'll get the theta L. So with this we get two things, MLRL and theta L. MLRL when divided by RL will give me the balancing mass required ML, and theta L angle can be calculated from this polygon. So with this we have completed the couple polygon and force polygon. The system of unbalanced masses is said to be completely balanced now when both the couple polygon and force polygons are closed. This is what is known as dynamic balancing. Now we will see a numerical and we'll try to understand how this can be done with values. A, B, C and D are four pulleys carried by a rotating shaft having mass 9 kg, 6 kg, 12.5 kg and 10.5 kg respectively. Eccentricity of each of the pulley is 8 centimeters. Plane B, C and D are at 0.99 centimeter, 1.19 centimeter and 2.13 centimeter from plane A. The angular positions of unbalanced mass B, C and D is 0 degree, 44 degree, 133 degree and 261 degree with reference to mass A. The system of pulley is required to be completely balanced by adding two masses in two different planes L and M at radius of 10 centimeter such that plane L is between A and B and at a distance of 0.32 centimeter from plane A. Plane M is at 1.35 centimeter from plane L. Find the balanced masses required in plane L and M and their angular positions. So remember that when it is written completely balanced in a problem, we have to make force polygon and couple polygon both. This is what is known as dynamic balancing. So we go ahead with the. So we once again prepare the table, a table that we have already talked of. The data are written in the table. We'll start writing A, L, B, C, M and D. Then we'll write the masses, corresponding masses for A, B, C and D. Remember that masses for L and masses for M are unknown. This is what is the point of the problem. We have to get these answers. Then for A, B, C, D, the radius of rotations are given 8, and for L and M it is given as 10. So those values are put up in the table. Now the next column in the table is finding the product M into R. So we find product M into R. MR for L and MR for M are unknown, so they have been mentioned in the red color. Now we have to decide L. This time we have to find, or we have to select a reference plane. So we take help of this side view of the planes. Let's see that for no reason right now we are selecting reference plane as L. Why it has been selected we can understand later. Because it is between A and B, so the distance between L and A will be written as minus 0.32. So we can see that here the distance between L and A is written as minus 0.32, that is on towards the left direction, and all distances on the right direction will be mentioned in the positive. So distance between L and B is 0.67, distance between L and C is 0.86, distance between L and M is 1.35, and L and D is 1.81. So these distances are written. Now knowing all these distances, we can find the next column, which is MRL. As MR for 4 masses is known, that is ABCD is known, and L for all the masses is known, we can find MRLs for 4 and 2 MRLs will be unknown. So that is how we write like this. And at the end we'll write thetas which are known to us. So all the angles are written. So theta L and theta M are unknown. Now our next step would be to make the couple polygon followed by force polygon, and from these two polygons we will find the balancing mass ml and balancing mass mm required. So to make the couple polygon, we will select the last two columns and we'll start making the couple polygon. As the MRL for A is -23, we'll draw in the negative direction. So we make a couple polygon, and the length of the vector CA will be equal corresponding to 23 and direction is negative. Then my next vector will be L vector. We ignore it, we skip it because it is 0. We go to the vector B. Vector B is 32. So we select a suitable scale and draw a line which is 32 corresponding to 32 length, and the angle is taken as 44 degree from horizontal, measuring in the counterclockwise sense. Then we'll draw a vector CC which corresponds to length 86 and 133 degree. Then we draw a vector which corresponds to 152 and an angle is 261 degree. And finally we join the arrow of the last vector and tail of the first vector to find CM. From this CM we find MM, RM, D, and we find the angle. So we can find MM, RM, D as 97 and angle as 38 degree. So we have ended up with couple polygon. Now we go on to the force polygon. To the force polygon, we'll start with the force polygon. We'll select the MR column and theta column. So MR column and theta column. With these two columns, we'll start preparing the force polygon. The first vector is A. So we draw a length corresponding to 72 at 0 degree. Then another vector length corresponding to 48 at 44 degree, vector corresponding to 100 at 133 degree, then vector corresponding to 84 at 261 degree, and 71.85 corresponding to 38 degree. Now let me bring to your notice that it is not necessary to follow the same sequence. You can alter the sequence, but it is preferable that we follow the sequence given in the table. And finally we join the arrow of the last vector and tail of the first vector to find the MLRL vector. So this way we find MLRL vector and we find the angle. Finding the two, we can now divide by the radius, which is 10, and we find balancing mass ml. So this is 120 and 228 degree, and finally ml we can find 120 divided by 12 kg, and mm as 71.85 divided by 10 as 7.19 kg. So now we will solve this problem by analytical method. I'll just tell you the steps to be taken. To find the couple balance, we resolve the couples into horizontal and vertical components. So firstly we take cos components of all couples m1 r1 l1 cos theta 1 plus m2 r2 l2 cos theta 2 plus so on up to MM cos theta m equal to 0. Next step would be to find the vertical components of MRLs M1 R1 L1 sin theta 1 plus M2 R2 L2 sin theta 2 plus so on up to MM sin theta m equal to 0. From these two equations we can calculate MM and the position, angular position theta m. Then further from MM we can calculate the unbalanced mass. Now on to the next step, which is force balance. In force balance we will take again horizontal components of MR and vertical components of MR. M1 R1 cos theta 1, M2 R2 cos theta 2, and so on up to ML RL cos theta L are the horizontal components, and M1 R1 sin theta 1 plus M2 R2 sin theta 2 plus so on up to ML RL sin theta L are the vertical components. From these horizontal and vertical components we will find ML RL and the angular position theta L, and from ML RL we can find ML as RL is known to us. And this is how we can do the dynamic balancing. If you have any doubts, please feel free to contact me. Thank you.